And now we are going to obtain the stoichiometric table for flow systems. The form of the stoichiometric table for a continuous flow system is virtually identical to that for a batch system, except that we replace nj0 by fj0 and nj by fj. Taking A as the basis, divide the equation for reaction given through by the stoichiometric coefficient of A, so we obtain that capital A plus the ratio of the stoichiometric coefficients B and A times capital B will give us the ratio of the stoichiometric coefficients C and A times capital C plus the ratio of the stoichiometric coefficients D and A times capital D. Entering, we will have FA0, FB0, FC0, FD0, and FI0. Leaving, we will have FA, FB, FC, FD, and FI, which is the inert. So, here we have our stoichiometric table for a flow system. In the first column, we have the species A, B, C, D, I, and the total of those. In the second column, we have the feed rate to the reactor in moles by units of time. We will have FA0. We will have FB0, which is equal to theta B times FA0. In the third column, we will have the change within the reactor in moles by units of time. For A, we will have minus FA0 times X, which was what reacted. For B, we will have minus the stoichiometric coefficient of B divided by the one of A times FA0 times X, and so similar expression for C and D, taking into consideration that those are products, so the change is positive and not negative. For the effluent rate from the reactor in moles by unit of time, which is the fourth column, we will have that FA is equal to FA0 times 1 minus X. FB will be FA0 times theta B minus the stoichiometric coefficient of B divided by the one of A times X. So we will have similar expressions for FC, FD, and FI. And at the end, we will have FT, the total molar flow rate at the end, is equal to FT0, the total molar flow rate entering the reactor, plus the relations of the ratio of D divided by A plus C divided by A minus B divided by A minus 1, all that times FA0 times X. And it will recall the relation of these stoichiometric coefficients, the sum and rest of these stoichiometric coefficients is delta, which is the increase in the or decrease in the volume due to the reaction. So we will have that Ft is equal to Ft0 plus delta times Fa0 times X. And we recall that theta B is equal to Fb0 divided by Fa0, but it's also equal to Cb0 divided by Ci0, or equal to Yb0 divided by Ya0. Equations for concentrations in flow system. For a flow system, the concentration Ca at a given point can be determined from the molecular flow rate Fa and the volumetric flow rate B at that point. So Ca, the concentration of A, will be Fa divided by the volumetric flow rate B. Rewrite the concentration of A, B, C, and D for the general reaction given in terms of the respective entering molar flow rate FA0, FB0, FC0, and FD0, and the conversion X and the volumetric flow rate B. So for CA, we will have that is equal to FA times B, and this is equal to FA0 divided by B, all that times 1 minus X. The concentration of BCB will be FB0 minus the ratio of the stoichiometric coefficient of B divided by A times FA0 times X, all that divided by the volumetric flow rate B. And so we will have similar expression for C and for D. Now, if we have the case of liquid phase concentrations, so we will have that for liquids, the volume change with reaction is negligible when no phase changes are taking place. Consequently, we can take that the volumetric flow rate at the exit is equal to the volumetric flow rate entering the reactor. So B is equal to V0. And then we will have that CA will be FA0 divided by B, all that time 1 minus X. But FA0 divided by B is equal to FA0 divided by B0, and this is equal to CA0. So CA is going to be CA0 times 1 minus X, and CB is going to be CA0 times theta B minus the ratio of the stoichiometric coefficient of B divided by A times X. And so we will have similar expressions for the concentration of B, and for the concentration of C and the concentration of D. And then we will use one of the rate laws, and we can find then the rate as a function of conversion for liquid phase reaction, and that's something that we are looking for, to have the rate as a function of conversion, and we will see that later on. However, for the gas phase reactions, the volumetric flow rate must often change during the course of the reaction because of a change in the total number of moles or in temperature or pressure. Hence, we cannot always use last equations to express concentration as a function of conversion for gas phase reactions. By example, reactions in the gas phase that have a change in the total number of moles. A situation where one encounters a varying flow rate occurs quite frequently in gas phase reactions that do not have an equal number of products and reactant moles. For example, in the synthesis of ammonia, we have 1 mole of nitrogen plus 3 moles of hydrogen will give us 2 moles of ammonia, and so we have 4 moles of reactants and only 2 of products, so it's going to be a decrease in the volume.